Okay, so this is our little review session here. Today is 1-3-17. That's weird. So we said electronegativity difference determines bond type. We've got some numbers that we filled in, and we want to know a little bit more about what those numbers dictate. So we're looking at words, types of bonds, and somebody threw out ionic. So we could have an ionic bond, polar bond, non-polar bond, is that right? Covalent. Polar and non-polar covalent. Okay. All right, so we now have sort of 3 to pick from. Of those 3 that we have to choose from, ionic, non-polar covalent, polar covalent, let's go back to here. If we're between 0 and 0.3, so there is almost no difference in electronegativity, what kind of bond would that be? Non-polar covalent. And if it's non-polar covalent, how are the electrons being shared? Evenly or unevenly? Evenly. This is 2 atoms that have nearly identical or identical electronegativities. They each want the electrons the same amount. They're going to share very evenly. Between 0.3 and 1.7, what do we get? Polar covalent. And if we have a polar covalent bond, how are they being shared? Evenly or unevenly? They have a difference in their level of love for electrons. Well, they share them evenly. Unevenly. This is uneven sharing. Maybe we should add that. Okay, and things that are polar covalent compounds that are held together with polar covalent bonds, what's so special about a polar molecule? What does that uneven sharing create on the molecule itself? Remember Mickey Mouse? We get regions of partial what? We get regions of partial charge. So one end of the atom, or one end of the molecule will have more electrons, and hence will have a little bit of a negative charge. The other one kind of gets the electrons stripped away, so it ends up with a little bit of a positive charge. Okay. Now, those are our covalent bond types. What if we're between 1.7 and 3.3? What kind of bond are we looking at there? Ionic. There's only one option left. Ionic. And ionic means what? How are they shared? That was a trick question. They're not! Okay, so in an ionic bond, there is no sharing. One atom strips the electrons off another, and that other one typically willingly gives them up, because these are things where there's such a strong difference in electronegativity. One really needs additional electrons to become stable, and the other really needs to get rid of additional electrons to become stable. Okay, do you feel like you kind of remember that now? Okay, do you remember QT? Well, do you remember what a molecule is? So a group of atoms, and it's specifically a group of atoms that's held together with covalent bonds. So group of atoms covalently bound. And moreover, it's a neutral group of atoms. Okay? So it's a neutral group of atoms bound with a covalent bond. They are sharing electrons. If they are not sharing electrons, it's not a molecule. There are no salt molecules. There's no sodium chloride molecule. It's an ionic compound. What do you remember about molecular formulas? In a molecular compound, the formula tells you the actual number of each kind of atom. It's different than in an ionic formula, and we're going to do both kinds of formula naming in the next chapter. But, H2O, that's the formula for water. There are actually 2 hydrogens and 1 oxygen in every molecule of water. C6H12O6, sugar molecule, glucose. There are actually 6 carbon atoms, 12 hydrogen atoms, 6 oxygen atoms. So that's the thing to remember about formulas. We left off talking about bond length, and we had talked about cutie pie and best friend. Where bonds form is a function of that dance. Do you remember what the dance is between? Think about cutie pie and best friend. Okay. It's a dance between attraction and repulsion. What's attracted to what? What's attracted to what? The protons, okay. Okay, we have forces of attraction between these protons and these electrons. Or, let's do a better job there, Moser. What's repulsed? The protons and the protons. There are proton repulsions. What else? What touches first? The electron clouds. So, you know, this electron cloud is kind of repulsive to that electron cloud, yet this electron cloud is attracted to that electron cloud. So the distance at which they form is where there's that balance between attraction and repulsion. And it's a dance, and you really have to understand bonding in those terms. Okay. So the distance between the 2 nuclei is the bond length. Did we get to here? So remember we talked about atomic radii. It's half the distance between the nuclei of 2 bonded atoms. Well, now what we're going to talk about is the entire distance, and that is the bond length. So if we have these 2 atoms, and it doesn't matter how big their electron clouds are, if they're sharing electrons, their electron clouds are actually going to overlap where they're shared. But the distance that we're interested in is the distance between the 2 nuclei, and that's the bond length. And bond length varies tremendously. It's typically measured in picometers. That's pretty common. So a picometer is, what, 10 to the negative 12th meters? It's pretty tiny. Chemical bonds contain energy. And bond energy, if we're going to go back to that sort of table that I drew for you. Bond energy is the amount of energy that's contained in the bond. It's given off when atoms bond, and you have to use that energy to break the bond. So to break 2 atoms apart requires some amount of energy. If they were more stable in a non-bonded state, they wouldn't be bonded. So it does take some energy to break bonds. Now there's also energy contained in those bonds. So when you break some bonds, you also release a lot of other energy. And we'll talk a little bit about bond energy and the energy in it. And I've got a funny story with a not tragic ending, which is good because it could have ended differently. So let's look back at that chart that I drew. Okay, so we've got these 2 atoms. They're separated from one another. They're attracted to one another. This is Cutie Pie! And, you know, Cutie Pie and you go running across the field to the strains of schmaltzy 70s movie orchestra music and a fuzzy filter. La, 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 la. You know, running towards one another because the force of attraction is so overwhelming. That force means that there's energy there. There is energy as those 2 are pulling together. So this thing is high energy. It's unstable. If you were holding on to those 2 atoms, they would want to pull out of your hands. Like if you're holding 2 powerful magnets and you're trying to separate them. Okay? It's not stable. If you let go, they're going to smack together. Well, in this case, if nothing stands in their way, these 2 atoms are going to go racing towards one another. And as they race towards one another, they become more stable, and their energy drops. And they get to a point where, hey, look, they're bonded, and they're low energy. Now, if they were to push past, push a little bit further, and sort of overshoot the mark, let's say. Copy this. And those two nuclei were to end up pushing up against one another. Would that be stable? No, because then you've got a force of repulsion pushing them back apart. So the point where they are stable is this low energy point. Low energy, stable. And that's what determines bond length. Now here's the thing that I probably should go off and diverge a little bit. Have you used energy diagrams at all? Because I want to talk a little bit about how to read an energy diagram. This is one of those skills that is useful for ACT, because on the ACT it's a lot of getting information from graphs. So even though you may not see an energy diagram quite like this on the ACT, being able to look at a graph and figure out what it's telling you is a really useful skill. So when we're thinking about this amount of energy, and I'm going to shrink these guys down. I'm going to sort of make this into a bar graph. I'm going to cheat a little bit. This is very high energy. This is much lower energy. There's a difference between these two energy states. Now, we don't have any units on this. But the question is, if something goes from being higher energy to lower energy, what happens to this amount of energy? Where does that amount of energy go? Where? Gives it away. Where does it go? Can anything just go away? Ever? No. It just goes out into the environment. It goes into whatever is nearby. So that energy is released to the environment. Now, if we think about that Gesundheit in the inverse, to take something from this energy level to get it up to that energy level, what would you have to add to the material? So let's think about this in a metaphor that's a little bit more approachable. How many of you have seen liquid water? I will assign homework if I need to. How many of you have seen solid water? Okay, good, excellent. So we can think about water and energy the same way. We can think about any material with phase changes the same way. And solid water has got about this much energy, kinetic, it's temperature, kinetic molecular energy. Liquid water, whoops, I have that all backwards. Solid water has this much energy. Liquid water has this much energy. And gaseous water, steam, has this much energy. Okay? So if you want to take something from being a solid to being a liquid, there's a difference in the amount of energy here. And if you want to take something from being a solid to being a liquid, what do you have to do to the material? Where do you have to put that amount of energy? Who here has ever melted a solid? What did you have to do to melt that solid? What did you have to do, Alexa? You added heat energy. So you had to actually add energy to the material. If you were going to freeze something, you would actually get energy out. When I was a kid, there were a lot of strawberry fields around here, and on cool spring nights, very often farmers would get out the irrigation rigs and they would spray water over the strawberry fields. And I remember as a kid going, why are they doing that? And my dad would say, oh, they're saving the crop. How do you save the crop by watering strawberries on a night when you're going to get a frost? In the morning, those leaves would be covered in solid frozen water. There'd be sheets of ice. They do the same thing down in Florida. When there's a heavy frost coming in before the orange crop is picked, they'll irrigate the orchards. How does that help? If you put liquid water onto the surface and it freezes, where does this amount of energy go? Out into the environment. If that liquid water is laying on top of the plant, what's the immediate environment that's going to get that energy? The plant, the leaves. So the water on top of the leaves freeze, but the water inside the cells doesn't, because they get this little sort of burst of heat as the water on their surface freezes, as it goes out into the environment. So I want you to be able to think about any substance and the amount of energy it has and moving it to some other condition. And the idea that to move a substance from one amount of energy to another, you either have to put energy into the material or you get some energy out of the material. So when we think about this in terms of chemical bonds, if we take these two atoms from being separate but attracted to one another, unstable, high energy, and we bond them, some energy goes out into the environment. If we want to break that bond, what would we have to do? We would have to put that amount of energy back into the material to sort of push it up that hill of stability. So we have to add that much energy to break the bond. We often say is that there's energy contained in a bond, and that's that bond energy. And it's given off when atoms break apart. Or it's given off when atoms bond, rather, and we have to put it into the material if we want to break the bond. Now, there are other energy relationships with bonding. So let's talk a little bit about bonds, bond length, stuff like that. So this is a table that's really similar to your book. This is bond length and bond energy. How much energy is contained in a bond. It varies widely. It's different from atom to atom. Now let me ask you this. Oh, and I just expect you to have this chart memorized by tomorrow. That'll be not a problem, right? Two fluorine atoms here. They each have 7 valence electrons. Second uppermost main energy level, 7 electrons. What do they want to be like? They want to be like neon. They want to have a full upper S&P, which would mean 8 electrons in that uppermost level. Well, they each need 1 more electron. So if they overlap their orbitals and they share 1 electron, that's all they have to do is share 1 electron, then suddenly each of them feels as though they have 8 electrons, because there's that 1 pair of electrons that they're sharing, in essence. So now if we count, well, they're actually sharing a pair. Hold on, let me undo that. The vagaries of drawing on here. There we go. So if they overlap their orbitals right there, and then we start counting, we get 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So everybody feels like they have 8, even though they didn't gain any electrons, but they're just sharing that 1 pair, so it makes it, they each feel full. Okay? This is a single bond. They're sharing 1 pair of electrons. That's all they're sharing. Well, we can do more than that. So carbon is cool stuff. Carbon has 4 sites for attachment. You're made mostly of carbon. Organic chemistry is based on carbon. Pretty much everything you eat is based on carbon. because you're a carbon-based life form. You need carbon molecules to make your body. And carbon has these 4 sites for attachment, so it does this cool thing where it can bond to 4 things. So carbon will bond to hydrogen. Let me draw a little hydrogen atom here. And it will share its 1 electron with a hydrogen. And hey, there you go. We're bonded. Darn it. And now carbon's, remember hydrogen only wants to get to 2. So carbon's now got 2 that feel like full pairs. It still wants 2 electrons. So the interesting thing that carbon does is that carbon will share more than 1 electron. And a lot of atoms do this. Carbon is just really well known for it. So what carbon will do is overlap orbitals and end up sharing more than 1 pair of electrons. And what we call that is a double bond. In a double bond, something is sharing more than 1 pair of electrons. So a double bond is 2 shared pairs of electrons. Do you want to take a guess what a triple bond is? 3 shared pairs of electrons. And carbon does this pretty commonly. There are a number of carbon compounds that have 3 bonds. And we show this. We have some sort of visuals for showing bonds. There's a single bond between 2 carbon atoms. There's a double bond. There's a triple bond. Now here's the interesting thing, and here's where I get to shoot rubber bands at you. So with the rubber band analogy, you can stretch a single rubber band much further. That distance is much greater. Double it up, the distance reduces. Triple it up, and actually if you can get your fingers in there, it's an even smaller distance that you can stretch it. Well, guess what's true about single, double, and triple bonds? Single bonds tend to be longer. Double bonds tend to be a little bit shorter. And triple bonds tend to be the shortest. Okay? They get smaller and tighter as you're sharing more electrons. They're held more tightly. There are different amounts of energy contained in those bonds. So who here knows what propane is? Who here has ever seen propane? Some of you will have homework. Okay. They sell little tiny propane torches. Have you ever seen little propane torches? Just a little thing, torch on the end. I should have brought one in today. Well, propane, monkeys eat peanut butter. Propane, 3 carbons. Monkeys eat peanut butter. Methane, ethane, propane, butane. It's how you remember the names of your carbon compounds when you're taking organic chemistry in college. And then it's like penta, and those are easy. But the first 4 are hard. So propane is actually just a 3-carbon chain, single bonds. It's like that. And it's got a lot of energy. How do we typically get the energy back out of propane? We light it on fire! That's how you get energy out of a lot of stuff. You light it on fire. The energy of those bonds gets broken as those bonds are being broken. Some of the extra energy gets released out into the environment. That's great. We use it to cook food. We use it to heat our homes. We use it to, heat up pipes when we're welding them. Fantastic. Well, does anybody know what MAP gas is? Have you ever heard of MAP gas? Well, so things like MAP gas are used because they burn hotter. They deliver more energy when you break down those bonds. Okay, this is in here, though. Really, we've kind of been addressing it all along. The octet rule. Oct means 8. And we know, we've been talking about the fact that a noble gas configuration is the stable configuration. It's what all the cool kids want to be doing. And typically, when we're talking about covalent bonding, ions too, but we'll talk more about that later, things tend to form so that everybody feels like they've got that full S&P. And this is the S&P block elements, the main group. D block is a little bit different. It's a little bit weirder. So we don't talk about that much yet. But for the S&P block, definitively, they are looking to get that full S&P. So they're looking for an octet of electrons, and they share to get to there. There are a few exceptions. We call them octet exceptions. When we start doing structural formulas, you'll need to keep these in mind. So hydrogen only needs 2 electrons to be stable. That's because it's only got one energy level. Boron, and I don't know why, and this is very weird, it's stable with 6. 6 electrons makes boron happy. Somebody knows why, but it's not me. There are some atoms that can actually end up surrounded by a lot more than 8 electrons and be okay with it and still feel stable. And it usually is related to what they're bonded to. If they're bonded to something that's kind of pulling some of the electron cloud off of them, that helps. So, and we call it expanded valence bonding. It happens in things that have got some D subshells where they can engage those. So, okay, we are going to stop here for today. I'm going to give you time to work on homework. Do we have the start of the assignment out? Yes.